Other applications are in chemistry, which is the neutron activation analysis. So in neutron activation analysis, this is a technique where it is an induced radioactivity by bombarding a stable isotope with neutrons. A great application for this one is in archaeology, wherein human bones before were bombarded with neutron, or ang sample is bombarded with neutron, like strontium for example. And the amount of strontium-38 would indicate kung pila ang amount of strontium in that. Why is it important? So they found out, class, that prehistoric human bones would dating them or measuring the amount of strontium in these bones would indicate kung unsa ilang diet. Plant-based diets contain higher strontiums in their bones because plants contain more strontium versus animals. So high strontium content in bones would indicate that the diet of that prehistoric human was largely vegetarian. So it also extends to unsa ang gender of that certain human bone. So from farming na communities, prehistoric farming communities, makita ng difference in sex. Women have higher strontium levels versus men because apparently in those days, women would stay home or stay in the communities and plant, thus consuming plant-based diet. Whereas men would spend more time away hunting and eating kung unsang ilahang gihunt or animals that they hunt. Thus, lesser strontium levels. So there are different elements. This neutron activation analysis could be used for 50 different elements as small as 1 picogram or 10 to the power of negative 12 gram. So it is both a qualitative and quantitative na analysis. It is qualitative because the gamma ray or the wavelength of the gamma ray produced is or differs from one element to another. And the quantitative amount could indicate different levels and opens doors for quantitative analysis, just like this one, strontium analysis or diet analysis in prehistoric bones. Other is for commercial applications like in smoke alarms. So smoke alarms na siya americium, typically americium 241, and that tiny amount of isotope is placed in the ionizing chamber where it decays or ionizes air molecules within the chamber. So, and with the influence of a potential applied by a battery, kanina ions would move across the chamber producing electrical current. So if air is blocked, na smoke na mo block, or smoke particles would get into the chamber, ang normal flow ani na ions is impeded or stopped. So ang electric current would then drop. So this trips the alarm and would send off, or it would make the smoke alarm go off. It also is the same if ang voltage sa battery mo drop or ni-decline na ang battery. That's why it is advisable for smoke alarm batteries to be changed about once a year or some even every 6 months. Another is in food preservation. Gamma rays, as harmful as they are, they could actually kill insects and larvae and parasites, such as the trichina, which can cause trichinosis in pork. So ang kanina radiation could also inhibit sprouting of onions and potatoes. As you know, when potatoes sprout or turn green, they are toxic already. They produce toxic chemicals when ingested or inhaled ang iyahang mag-give off na vapor. One of the most important jud in food preservation is extending the shelf life. So we know that there are some preservatives that can be added to extend the shelf life of certain food. But since they have adverse health effects, irradiation is an attractive na alternative. It is a considerable alternative. It can destroy E. coli and different microorganisms and even anthrax. That's why in some government agencies in Western countries or European countries, they sterilize ang ilang packages o ang ilang letters or ilang mail to kill off potential biohazardous threats or biological na terrorism. Because some terrorist groups have used anthrax before to try and infiltrate government agencies. So it's so cool to know that there are a lot of ways to harness this murag essentially deemed harmful na subcategory in chemistry to our advantage, both in food and our safety, and to understanding or mapping ang behavior and socio-economic behavior of prehistoric human beings. Now let's proceed to computations regarding rate of radioactive decay. So the rate of radioactive decay is or indicates how fast a radioactive isotope decays. So we have the following formula. We have rate is equal to Kx, where X is the amount of radioactive species present at that certain time, and K is the fraction of atoms decaying in unit time. So the unit for K is usually S negative 1 or over negative or over S. It's the same. Half-life is usually in years or seconds or in minutes. And then we have ln or the natural logarithm. Asa na makitaan, it is found in your calculator. ln xo over x is equal to kt. K is equal to 0.693 over half-life, or the amount of time that that certain isotope, the amount of that certain isotope is halved. We also have the formula for activity. Because of the way in which the rate of activity is measured, it is often described as an activity of a sample, which expresses the number of atoms decaying in unit time. Using this equation, A is equal to K times N, where K is the first order rate constant, the same with the previous na formula, and N is the number of radioactive nuclei present, usually in atoms. So the A activity is expressed in number of atoms per decaying or decaying per second. Or it could be in becquerel, which is equal to 1 atom per second, or in Curie, which is equal to 3.7 times 10 to the power of 10 atoms per second. So let's try and apply. Let me remove all of this. So in this problem, the half-life of radium-226 is 1.6 times 10 to the power of 3 years, or that's equivalent to 1,600 years, or 1.5 times 10 to the power of 10 seconds. Yun sa pag-convert. 1,600 years. So in 1 year, 365 days. In 1 day, 24 hours. 1 hour, 60 minutes. 1 minute, 60 seconds. That's a conversion to get this value. Question is, calculate K in S to the power of -1 or over S. So the formula for activity is K times N, or you could directly use K is equal to 0.693 over T1 half. So asa may mas applicable? It is more applicable to use this equation. Why? Because you're already given your half-life. Now, just directly substitute. K is equal to 0.693 divided by your half-life, which is 5.05 times 10 to the power of 10 seconds, equals, your answer should be 1.37 times 10 to the power of -11 as -1 or 137, 11 over S. This is the value or the rate, imuhang rate, for rate constant in the first order reaction. Next question. What is the activity in curies of a 1 gram sample of radium-226? So 1 curie is equal to 3.7 times 10 to the power of 10 in atoms per second. So activity is equal to K times N. We already have K from the previous, which is 1.37 times 10 to the power of -11 per second. Your N How do we get your N? From 1.00 gram of radium-226, you could convert that using the mass. And then using Avogadro's number as well. Diba? Remember this? Cancel. You will get 2.66 times 10 to the power of 21 atoms. Substitute everything. Just simply multiply both values and you will be able to get an activity of 3.64 times 10 to the power of 10 atoms per second. These are your units as shown. Di makancel. Now, the question is in curies. So let's use this formula. Let's use this conversion. Converting 3.64 times 10 to the power of 10 atoms per second. So according to the conversion factor, 1 curie has is equivalent to 3.7 times 10 to the power of 10 atoms per second, or 0.985 curies. So this is the activity in curies. Next, letter C. What is the mass in grams of a sample given the activity of 1 times 10 to the power of 9 atoms per minute? So again, you are asked for mass in grams. This time, you could use the same equation for activity. Ano man, we will be looking for N. We'll be looking for N. We will convert N to grams. So how do we do that? We already have the activity. So N is equal to A over K. Your activity is given. However, it is, by the way, in atoms per minute. So let's convert this one first. Per minute to atoms per second, 1 minute, 60 seconds. So that's simply going to be 10 to the power of 7 atom per second. So substitute. K is from the previous in letter A. We already calculated this one. If you don't trust that, you could calculate it again. It's just the same given. Cancel S, you'll be left with atom. 1.22 times 10 to the power of 18 atoms of Ra226. Now, we are asked to get the answer. We are asked to get the answer in grams. So let's convert it to grams. 1.22 times 10 to the power of 18 atoms, Ra226. That is 6.022 Avogadro's number. And the mass of Ra226. That should be equal to 4.58 times 10 to the power of negative 4 grams. That is your answer. Now, ang curie was supposed to be the activity of 1 gram sample, and it is discovered by both Marie Curie. So, let's proceed to the dating of organic materials. We're almost done. So, Professor W.F. Libby in 1950s in University of Chicago worked with a couple other people to work out a method of determining the age of an organic material. Organic materials usually contain carbon. So, it is based on the decay rate of carbon-14. So, kanina method is applied to objects from a few hundred up to 50,000 years old. And it has been used to determine ang authenticity of a couple of paintings of some Renaissance painters and to check the ages sa mga relics or archaeological finds left by mga prehistoric dwellers in caves, for example. So, ang carbon-14 is produced in the atmosphere by the interaction of neutrons from cosmic radiation with ordinary na nitrogen atoms. So, nitrogen reacts with um, nitrogen reacts with neutrons from cosmic radiation, producing carbon-14 and hydrogen. So, ang carbon-14 formed by this nuclear reaction is eventually incorporated into the carbon dioxide in the air. So, at a steady state concentration, amounting to about 1 atom of carbon-14 for every 10 to the power of 12 atoms of carbon-12, it is established in atmospheric CO2. So, more specifically, class, ang gidaghanon or the amount of carbon-14 or concentration in a sample containing 1 gram of carbon has the activity of 15.3 atoms per minute. So, a better example is that a living plant that is taking in carbon dioxide, of course, because it takes carbon dioxide, or a food for plants is carbon dioxide, or it intakes carbon dioxide from the atmosphere, na siya same na activity. So, it takes 15.3 atoms per minute. And as do mga animals that would eat these plants, and even human beings. So, when kanina plant or animal would die, mag-stop na silang intake, of course, sa carbon or radioactive carbon. Wala sila nag-inhale, wala sila nagkaon. So, consequently, ang rate sa decay sa carbon-14 would then be, it would go back to nitrogen and release another electron. So again, ang iyahang half-life is already established. 5,730 years. And ang carbon-14, because ni-stop naman ang intake, mo-decay or mo-decompose na katong tanan na carbon-14. And ma-measure, that's when ma-measure na sa different scientists and through calculation. And ang activity sa carbon-14 would drop. The activity of the sample is directly proportional to the amount of carbon-14. So, we can derive this formula. Ln is activity or AO, which is the original activity, assumed to be 15.3 atoms per minute, assumed ha, and A is the measured activity today. T is the age of the sample. So, if you could get the age of the sample by multiplying K, Ln, AO, A. So, let's try this out. A tiny